Over.
Tak, começou.
Okay. All right. All right, so let's start with today's lectures, which is about Dyson-Schwinger equations and word identities, which are all relations between various types of Green's functions, relations that encode some of the classical symmetries at the quantum level. So we will start with something classical, and then we'll try to write something similar at the quantum level. And in so doing, we'll be obtaining some relations between Green's functions, which are our basic objects. So let's start with Dyson-Schwinger equations. Well, classically, the first thing we say, we have the equations of motion, classical equations of motion. And by the Ehrenfest theorem, we expect those to be valid as vacuum expectation values, to be valid on the average. So let's say in quantum mechanics, because of the Ehrenfest theorem, valid on the average. So so valid on the average. So one important observation is that valid on the average really means taking the average here and not just on the field. So of course we know that we call the classical field the quantum average of the field, but what we're saying here is that actually, by the Ehrenfest theorem rather, what it says is that the equation itself should be valid on the average, not in terms of average fields. And well, we'll be working on a path integral formalism as we did the last few lectures, since this is so much easier to derive all the equations that we will derive. But they were originally found in the operator formalism, and there it looked kind of complicated. But here we'll see that we find an almost trivial set of equations. So basically, we start with this trivial observation that if we have an integration such that the boundary terms are either zero or periodic, that is f plus infinity equal to f of minus infinity, then the integral of a derivative will give zero. So, of course, we have to generalize this to path integrals, but that is not a problem. So, in our case, we would write that a path integral, and then the equivalent of ddx, now we're talking about functionals, right? So things that are functions of functions, so we have to take the functional integral, functional differentiation, sorry. And here we take the basic path integral, so e minus s, and also with a source of plus g dot phi. This should be equal to 0, since as we know, the correct definition of the path integral is in Euclidean space, with a time being periodic with very large radius. So, since there is periodicity in time. Okay? Okay, so now we write explicitly what this means. So taking the derivative, we get minus ds d phi, first term, and j. This is equal to 0. And further, we do what we did before. So this is still a function of phi. So it's first derivative of the action with respect to phi, but it's still a function of phi. And then, since we have these phi's outside the exponential, and we have this term e to the j phi, we can replace the phi's with derivatives with respect to j. Since by taking a derivative with respect to j, we pull outside the phi. And this is also equal to d phi minus ds d phi at phi is equal to dej plus j minus s phi plus j phi is equal to 0. And now in the bracket here we have only things that depend on j. And this is called the basic, this is the basic Dyson-Schwinger equation. And as of yet it doesn't look like it, but by taking a bunch of derivatives, we will be writing this as an equation between Green's functions. But the first observation I want to make is that this is, as I said, it's an almost trivial equation. The way we derived it, it looks completely obvious. But when people try to derive this in the operator formula, it was not so trivial. All right, so now to continue, we will specialize to our favorite case with a canonical kinetic term and a polynomial potential. So let's write S of phi, and also we'll consider discretization in order to have some simpler formulas. So discretize and canonical kinetic term. This with the kinetic operator being an inverse propagator, having in mind that phi I in principle could be something else than a scalar, although this is what we write this for. And then the thing that we have in here is ds d phi, but we can also, in the discretization, this would be ds d phi I, because phi of x becomes phi I, right? But we will also be multiplying with a propagator to get rid of that inverse propagator. That's otherwise a bit problematic. So let's consider then this object, right? So when we take derivative here, we get delta minus 1 phi, multiply by delta, we get just phi, right? Phi L. Then here, we get the same. All right. So now we write the Dyson-Schwinger equation. And yeah, so I forgot to say the last step in here, this is a path integral over phi. So the path integral can be put on the right hand side. And then this, because this is just a function of j, so this can be pulled out. And so we can write minus ds d phi at phi equal to dj plus j of x acting, and then the path integral itself is z of j. Right? So now substituting this over there. So remember that we have been multiplying by delta this equation. So we have this delta dot del s del phi applied when phi is equal to ddj. So then with a minus in front as well. So we get minus ddj L, let's call it. Phi L becomes ddj, and then this we have this thing with a minus sign. And then minus this second term, sum over I, delta Li, equals I, d phi I, and phi is ddj. And then plus j. Okay. Okay, so we can also write this. Oh, sorry, I forgot to multiply by delta. Delta L I J I. And well, I can separate the derivative with respect to j and write this as then dz of j djl is equal to this term, so delta li ji z of j minus delta li dsi d phi I, and phi is equal to ddj. And I separated it this way because this is what I want to emphasize. Excuse me. So here I have one derivative of the partition function of z of j. And here, so this is an interaction term, right? So this will have, as an interaction, it will be at least phi cubed. Means dd phi will be at least phi squared. So this will, when I replace, I'll have at least two derivatives acting on z, right? So I relate the first derivative with respect to j of z with the second derivative, or higher. And then from derivatives of the partition function, we get Green's functions. So this is why we'll get this equation relates one Green's function with a higher Green's function. Okay? And to continue, so this would be the basic one. But to continue, to be more precise, we'll choose an interaction term. And since in 4 dimensions, well, the most interesting thing is phi cubed, phi fourths, sorry, and then it's and then perhaps we could also think about phi cubed. So we'll take this linear combination of phi cubed interaction. And remember, this is this term, so when I discretize, it becomes a sum over phi I cubed. Here, a similarly constructed phi 4 interaction. So now let's write this specifically for this case. And derivative of this with respect to phi I will get, let's write both terms in a bracket. So here I'll get a factor of 3 that turns this into g3 over 2 factorial phi I excuse me, phi I squared, but phi is afterwards replaced with ddj, so let me do that already. So write ddji squared, and then similarly from here g4, a factor of 4 from the derivation cancels the 4 here, so we get g4 over 3 factorial, and then remaining phi cubed is replaced by ddj cubed, acting on z of j. Okay? All right. But we still want to see this as a relation between various Green's functions. As it is, this would be just a 1-point function, and here we'll have the 2-point function and 3-point function. But we want to write the general relation, so we'll take several more derivatives on this equation. So for the general case then, we'll take, we'll put first L equal I1 and then dj I2 until ddj In, such that in total on the left hand side we'll have n derivatives on z of j. So dn dj I1 dj In of z of j is what we call the n-point function. That's the definition of the n-point function. Sorry, yeah, when I also put j equal to 0. So this and then put j equal to 0. Well, I mean, in principle, I can define also the, as we did, the Green's function is the presence of non-zero j, but it's not particularly useful at this point, so let's consider just j equal to 0. And then, as I said, on the left-hand side, we define things such that we get this n-point function. And when I put j equal to 0, this first term goes away. And then we're left only with this term coming from the interaction. And so now we have I1, so let's write this specific, so minus sum of I. And then delta Li, but L is I1, so I1I. And here, G3 over 2 factorial. And then here I have ddji, ddji. But on top of that, we still have this n minus 1 derivatives, which will then get us to the Green's function with n minus 1 plus 2, that is n plus 1. Indices. The first indices are I corresponding to the two derivatives. And then we have these further indices I2 until In. And here, the same G4 over 3 factorial. This is one more index I. So this is n plus 2, excuse me, I2 until In. Okay. No, sorry, what did I do? No, sorry, yeah, I forgot one term. Yes, so I have to put j equal to 0. I have to put j equal to 0 only after I take these derivatives. Sorry. So, so that means that the only possibility is that one of the derivatives act on j. If all of the derivatives would act on z, it will be multiplied by j, which will give 0 at the end, which is what I got confused at the beginning. But we still have this possibility that one of the derivatives acts on J. And which one, depending on which one, we get a different kind of terms, right? So, one possibility, let's say the first possibility is the first derivative, I2 gets here, and in this case we get delta Li, and then delta I2, but I can do this sum already, and that is to say I just replace the index I with I2, and then the other n minus 2 derivatives act on Z, giving an n minus 2 point function. Indices I3 until In. So that's one possibility. Then another possibility is that the derivative acting on J is I3. So this will similarly give delta Li3, G n minus 2, and then I2, I4, In, and a bunch of terms like this until the possibility where In acts on Ji, then I get delta Lin, G n minus 2, I2, I3, In minus 1. Okay? So these are the possibilities. All right, so let's write down a diagrammatic equation for this. So let's define the endpoint function as a box with n legs sticking out. Just that, as you see in here, I1 has a special role to play. It's the index that appears on the propagator delta in here, right? Yeah, sorry, it was not L here, it was in the end I1. Or in other words, yeah, so everywhere on the propagator, both here and here appears on the propagator. So that means that we have to consider out of the endpoint function to write separately one of the legs. So we'll write that corresponding leg I1, we'll write it to the left. Just as a reminder that this is the special leg we choose in order to write this Dyson-Schwinger equation, right? So, so this is the endpoint function. As I said, in principle, I could have written all the legs on the same side if they were equivalent, but I want to single out I1 to write that Dyson-Schwinger equation with respect to this I1. And then what happens here? Well, here I have so yeah, okay, I'm supposed to write these terms first. So let's consider them first. So here I have one possibility is that out of these n indices, two of them belong to a propagator and the other ones form an n minus 2 point function. This was an n point function. And then we get a bunch of terms here where I1 is connected to each of the possible other indices, I2 until In. So one possibility is then for this n minus 2 point function, and then I1 is connected to one of the indices that we had. So the first possibility is with I2, and then from 3 to n they are on the endpoint function, the Green's function, sorry. And then another possibility would be with I3, so write it like this, I2, but then I1 goes until I3, and I4 until IN, until the last possibility, I2 until IN minus 1, and then I1 is connected with IN. So all of these were n minus 2 point functions. And then I have these terms. So the first one would be with a factor minus 1 over 2 factorial. And then I have a propagator from I1 to another I. And then here I have an n plus 1 point function, but two of the indices are the same. They go to the same point, and moreover it's the same point I in here. So we have two lines sticking out, and all in all 3 lines converging on this point I, because this came from a 3-point vertex, right? And then, so this would be an n plus 1 point function. 2 indices are here, but on the right I'll have the remaining n minus 1 indices. So I2 until IN. And the similar term with a 4-point interaction. So again, from I1 to a point I integrated over. This is a 4-point interaction, so one leg was already taken care of, and 3 remaining legs are on the n-point function, on the n plus 2 point function. So this is now n plus 2. And here I have I2 until IN. Okay? All right. So this was the Dyson-Schwinger equation, written as a diagrammatic expression. And now you can understand why this was somewhat complicated to obtain in operator formalism, because people started from diagrams. So they started from things like this, only with Feynman diagrams, not just a full endpoint function, and then it would be a bit more complicated to derive. All right, but why is this interesting? Well, I mean, of course, it's interesting partly because it gives a relation between different Green's functions. So, you know, equations constraining Green's functions are certainly interesting. If you know one, you know a little bit about the other. But moreover, it offers the possibility of iterating the Dyson-Schwinger equation. And, well, see what happens. We start with the endpoint function, and then we write things in terms of lower endpoint function, n minus 2, and higher, n plus 1 and n plus 2. But then we can iterate this, and when we do this, we obtain a kind of Feynman diagram expansion. So we get some propagators and then some other things. So by iterating it, in fact, we'll find the full perturbative expansion. And this is useful because this is actually an algorithmic way, another way of saying one that you can implement on a computer, of generating the full perturbative expansion. All right. So we wrote here the general Dyson-Schrödinger equation for the two-point function, but of course you have to start somewhere if you want. So if you want to write the equation to find a perturbative expansion for a given n-point function, you have to start with that. So the one that is most commonly used is the propagator, the two-point function, for various reasons that it can give you the exact mass states and many reasons. But anyway, it seems like a good starting point. We'll start with n equal to 2. So we write this Dyson-Schrödinger equation for the n equal to 2 case. So I1, I2 is equal to, well, in this case there's only one term where I connect two indices with a propagator. That's delta I1, I2. And then I get the 0-point function or partition function. And then I have the interaction with an integrate over index I, so delta I1 and then G with n plus 1, which would be 3. Then I to have the 3-point interaction, 3 this is I, and I2. And finally, no, write it here, minus G4 over 3 factorial, the same thing with a 4-point interaction. And 4 I2. Okay, so this is the equation, the Dyson-Schrödinger equation for the two-point function. I've written it in terms of the 0, 3, and 4-point functions. Okay, so iterating it means doing now the Dyson-Schrödinger equation for these guys. So I cannot use it for this because it doesn't have indices. The Dyson-Schrödinger equation relies on having one index being special, right? This one has no indices, so I cannot write it for it. But anyway, this is the vacuum bubble diagram, so this is not so interesting anyway. All right, so now I want to write an equation for this, and let me write it more to the left. So for this and for this, right? And also remember that Dyson-Schrödinger equations makes special one of the indices, so I have to decide which one, and well, we'll decide to be the first one. Okay? So now I write again a propagator that connects the special index with one of the others. So the first possibility is to connect these two i's, so delta I. Then I get G1 I2. Well, the other term would be when I connect I with I2. G1 I. And now these interaction terms. So from I to some other sum over index, let's call it J. G, now n plus 1, so that's 4. J, to have 3 indices for the 3-point interaction. And the remaining ones, which are I and I2. And then minus G4 over 3 factorial, delta Ij, G5, Jj, I2. let's see if I did things correctly. I2, J. No, this was, I didn't. Yeah. No, wait. Yeah, there was one J, and only one I left. Yes, because there were I2. So I have I2, and then 4 J's. Okay. And now for this thing, we repeat the same thing. Basically, I just insert one more I. But also, I have one more term now because I have two possibilities of connecting with an I, so there will be a factor of 2. Right? I mean, I could write the same term again, but the point is, the first thing is connecting I with one of the other indices, and I have two possibilities to connect with another I index. And then delta I2, G II2, and then minus G3 over 3 factorial, delta Ij, G5, JJ, I2, minus G4 over 3 factorial, delta Ij, G6, JJJ, I2. Okay? All right, and let's represent these three equations. Let's write down the diagrams for them. All right. So the first one, so the original one that I want to iterate is for the 2-point function, and the first term is I connect I1 with I2, and then I'm left with a 0-point function. And then I go from I1 to a point I that then connects to a 3-point function. And then minus 1 over 3 factorial from I1 or I that connects to a 4-point function. And then the iteration, meaning writing an expression for these things on the right hand side. So we write this is equal to. So I connect, the first possibility is connecting the external indices, which leaves here just which leaves here just a 1-point function. So say like this, I1, I2. No, sorry, what am I doing? Yeah, I want to I don't have the propagator. I just want to write this bit without the propagator. So here I have I. Here I have I2. So the first thing is to have a propagator. Let me, since I did this in my notes as well, let me separate these indices, but having in mind that they're both in index I. So write it like this, but I have in mind that they're both at the same point. So the first possibility is this, but the second is this. And
Professor,
yeah.
Are you forgetting the 1-point function?
Yeah, the 1-point function. Oh, this one.
Yeah.
Sorry. Then minus 1/2 a propagator times then J I still have the other I, right? And then minus 1/3 factorial. Same thing, where I go from I to a J. There's one more line coming to the same point. And then I2. Okay? So this is a 1-point function, this is 4-point function, this is a 5-point function. And now,
why do we omit the terms in the G3 and G4 terms that are multiplying the diagrams?
I'm sorry?
Intentional? The G3 and G4 terms.
Yeah, we're doing the G3 and G4, yes.
No, you just write 1/2 factorial instead of G3/2 factorial.
You mean the coupling? Well, whatever, yeah, you can put the coupling if you want. Yes. It's the same capital G and little g, sorry.
Oh, right.
I2.
Little g, sorry.
So now we calculate, so this would be 3-point function. 4. So now we write this 4-point function similarly, and then, as I said, we have two possibilities of connecting this I with another one of the I's. But then we're still left with another leg. So that's one term. Then another possibility is connecting I with I2. But then we're left with this 2-point function with indices I. And then minus 1/2 factorial times going from the initial I to a J if it's a 3-point function, I split to 2 more, and then I still have this 2 more indices I, and going to I2 on the right hand side. So now this is 1, 2, 3, 4, 5-point function. Minus 1 over 3 factorial, going from I to j, which is now a 4-point interaction. So I have 3 legs on the right, and then I still have these 2 legs I remaining here, and the leg I2 on the right. So this is 1, 2, 3, 4, 5, 6 point function. Okay, so these are the expansions of the terms on the right hand side of the original equation. And now for the iteration, I just substitute this, right? For the iterating step, I substitute these G3 and G4 into the first equation. So first, let's write the algebraic form. So G2 I1 I2 is equal to delta I1 I2 G0 minus G3 over 3 factorial. And now instead of that G3, I write the expansion. So I still have delta I1I, and then instead of G3 I have the expansion, so delta II G1 I2 plus delta I2 G1I minus G3 over 2 factorial delta ij G4 jj I2 minus G4 over 3 factorial delta ij G5 jj j I2, and then minus G4 over no, this was 2 factorial, sorry, 3 factorial delta I1I, and now I substitute also G4. So this is 2 delta II G2 I2 plus delta I1 I2 G2 II minus G3 over 2 factorial delta ij G5 jj I2 minus G4 over 3 factorial delta ij G6 jjj I2. All right, so this is the equation, and now let's write it diagrammatically. So diagrammatically, I could just look at these diagrams and basically substitute this on the right hand side. So let's write this. All right. So now I have this propagator times this. So let's do this. The first term is a propagator, and then in here this is the same point, so it's a loop, right? As I said before. And then times the one point function. Second term would be I1 until I, then until I2. But from I also have this one point function. Okay? Then write it here. Then I have these terms, so minus 1 over 2 factorial, propagated from I1 to I. Then I have one leg here, and then another leg that goes to another vertex, and then branches it off. I2. Then minus 1 over 3 factorial, I1 to I. Then I have the three-point interaction, but then and this one leg goes all the way to the 4-point function. And then this one has a 4-point interaction, so 3 legs going into it. Okay. Then minus 1 over 3 factorial, one more bracket. Now again, I have a propagator going to this I, and here the first thing is the same possibility to have a loop, just that now besides the loop I also have another point here. So point I has a loop and also another line sticking out, and then goes to this 2-point function. Then the other possibility is I1 goes to I, but then from there on one leg goes to I2, and then 2 more legs go to the 2-point function. Then minus 1 over 2 factorial, this term here, so the propagator goes to I. Then from I have 2 legs going to the Green's function, and 1 leg going to a J, that's now another 3-point interaction. So this is a 5-point function. And then finally minus 1 over 3 factorial, where from I1 I go to I. And then, as before, 2 legs go directly to the Green's function, and 1 leg goes to J, just that now this is a 4-point interaction. So this gives a 6-point function. Okay, so this is the iteration of the Dyson-Schwinger equation. All right. So the Dyson-Schwinger equation for the 2-point function is written in terms of 0, 1, 4-point, 5-point, and 6-point functions, right? But the interesting thing now, since what I want in this iteration is to find a full perturbative expansion, right? Then I take this equation and I consider it diagrammatically. So I consider a certain order in the coupling constant on both sides. So, so just to see something simple, we'll consider up to order G3 0, but G4 to the 1. So just one coupling G4, right? All right, so so this 0-point function, this first term has a 0-point function. So let's write this. Remembering, I only consider up to this term. So one 4-point interaction in here means one 4-point interaction in the 0-point function. So in the 0-point function, only one 4-point interaction, which means the only possibility is this one, right? So this I would write as or rather I should say 1, which is the order 0 plus this. So this would be 1 plus G, and here delta 2 propagators if I call this point K. Okay? Then I would say then I look at this, and here I remember that in fact, so perhaps it would have been good to write specifically that this was a G3, right? So so this does not contribute because we're looking at order 0 in G3, order 1 in G4. So for our consideration, I don't consider this first bracket, only the second bracket, which comes with a G4. All right? R minus 1/3 factorial G4. And then these terms, the last terms, comes with extra vertices, right? This comes with an extra G3, this comes with an extra G4. So these will not contribute because we're looking only at the order having 1 G4, which we already have. So 1 G4 is this one, right? Or this one, or this one, right? So so what can happen here then? Well, I already have this I think I forgot a factor of 2, right? There was a factor of 2 here. Yes. Because there were 2 possibilities of joining 2 of these eyes. It's crucial. I'm actually chasing numbers now, so we have to be careful.
So in the notes there's one more diagram that maybe it's the identical.
Yeah, right. So I write this diagram twice. So the only possibility then, since I already have this G4 in here, right? This G4 is associated with this vertex here. In here, I can only have a propagator for this 2-point function. And here is the same thing. For this 2-point function, I can only have the propagator. which moreover has the same endpoints. So the result is, I don't even need to put G4 because it's implicit in the fact that I write it like this. Right? That's why I didn't put G3 and 4. It's implicit. If I write the final diagram with this, I understand that there's a G4 in here. And then this goes all the way to I2. And this comes with a factor of 2. And the second one is where I go from also I1 to I2. But then you see I get the same thing. I get also a blob. Let me put it down just to make clear that it comes from the second diagram, but it's the same diagram, right? So this is just 3 times this, right? So the 3 cancels here, and I have 1 over 2. So in other words, by iterating this Dyson-Schwinger equation, I get that this is equal to this minus 1 over 2 this. Okay? So note what I have obtained. Well, I have obtained the correct symmetry factor because this has 2 lines which I can switch. So in this case, the iteration allowed us to obtain the all the Feynman diagrams, relevant Feynman diagrams, with the correct symmetry factors. Right? So that's the usefulness I hinted at, because this is an algorithmic procedure. You can just put it on a computer and it will generate all the possible diagrams with all the symmetry factors, correct symmetry factors. Okay. Oh, and another point is that I only showed you how to do the Dyson-Schwinger equation for the full Green's functions. We have this disconnected piece in here, but you can write Dyson-Schwinger equations as well for the connected or even for the 1pi Green's functions. The logic is exactly the same as I've done here. I'll not do it, but in principle, this can be done. All right.
The symmetry factor of this, the first part, that when you have 2 loops, yeah.
What's?
Don't you have to have a factor?
Oh, right. Yeah, okay, so this, I was not careful with this. In fact, in the notes I didn't even write it, I suppose. All right, so let's be careful with this as well. Yeah, I mean here, okay, so here I have to just count so how many ways I have to connect. So this I would just say, this comes with how many diagrams I have in order to connect 1K with another. So I have 3 times 2, right? The first one I have 3 possibilities, the second I have 2. So this comes with a factor 3 over 3 times 2, which leaves a 1 over 4, which is the correct symmetry factor, right? All right, so if you want, this is it. But
so this doesn't come from because
no, it comes, but I mean this is for the 0-point function, for which it's trivial. I'm just writing a Dyson-Schwinger equation with a single term, right? And then I just count. Okay. Good. All right. So now let's move on to symmetries and word identities. So let's repeat another theorem. I mean, you're supposed to know this well, but we'll do it here because it's better to see everything in one place. So the another theorem applies to global symmetries. And so if I have a global symmetry, I'll write it in this way. The parameter epsilon A, and then the generator that I call ITA, within this is IJ, and phi j. So this would be my symmetry, and these are constants. And under such a symmetry, the variation of the action is supposed to be 0. That's the definition of the symmetry. But this in turn is written as the variation of the Lagrangian with respect to the fields times delta phi plus the variation with respect to the derivatives times the variation of these derivatives. And then I can add and subtract a term with a derivative. So I want to obtain the equation of motion acting on delta, multiplying delta phi. So delta phi dl d phi d phi I minus d mu dl d mu phi I times, yeah, I perhaps, no, I mean write it like this. So, so this being equal to 0 is the equation of motion. But then I subtracted this term, so I have to add it back. But then you note that this is just forms the total derivative of this times delta phi, because here I have derivative acting on delta phi, here I have derivative acting on this first one. So I have plus d mu acting on del variation of L with respect to d mu phi I and delta phi I. Okay, so on shell, I vanish the first term, right? So now let's write this explicitly. So on shell, I'm left with just this, and then delta phi is this thing, and in it I have epsilon and ITA. Well, no, I just I epsilon and I. I think I want to take outside the derivative. So I say that so 0 is equal to integral d for x, and then I have this variation, which is I epsilon a d mu of delta L d mu phi I, then TA ij phi j. Okay. And from this I obtain the fact that this is called the current. This is the current associated with the symmetry, right? And on shell, I have that 0 is integral d for x I epsilon a d mu. J mu a. But since this is valid for all variations, follows that d mu a is actually equal to 0. So if we are off shell, however, so the equations of motion are not satisfied. So off shell, I get that delta L is this thing plus the term with the equation of motion, right? Just that the term with the equation of motion still came with delta phi in front, right? And so in delta phi I can still substitute the symmetry transformation and take out I epsilon a, dA. Okay, and then I'm left with the Lagrange equations. And here I have delta phi, I've taken out I epsilon dA, so I'm left with just phi. And in the second term, I have d mu of this thing. So dl d mu phi I phi j. Okay. Okay. So next I can I can promote epsilon a to a local one. Though, of course, if the symmetry itself is only global, that means this is not 0 anymore, right? So delta S is different from 0 because the symmetry is global. Okay? But if I do so, then I obtain that delta S is equal to so I get the same term as I've written in here, so let me not write things. Yeah, I can already note that this was what I called J mu A, right? No, sorry. No, what I'm saying. No, I want to call this. Yeah, I want to call this term just Sij. So this would be I integral d for x, I epsilon a of x, ta ij, Sij. But then, now if epsilon is a function of x, I cannot just pull it out. So I have to remember that in here, so in the second term, I had the derivative outside and delta phi inside. So there was a term with d mu acting on epsilon. So I have this one plus then the term that is actually d mu j mu a. And then I have a term which is d mu of epsilon a times, but what multiplies it is actually the same j mu a. The thing that multiplies it was the current, because this current term contained both, contained the derivative on the whole thing, acting on j mu a and on epsilon a. So I have this term plus the term where it acts on epsilon. Okay? In other words, now, remembering that we have also so global symmetry, we just saw that implies that d mu j mu a is equal to 0, right? Then delta S on shell becomes just this d mu epsilon term. And also, with a map. And also, if I want to, I could partially integrate in the case that I make epsilon a at infinity 0, right? We can partially integrate and say that this is minus I integral epsilon a d mu j mu a. But this is the important point, that I can identify the current as the coefficient of d mu epsilon in the variation of the actual. Oh, sorry. Wait. No, I did something wrong. What did I say in here? No, sorry. I actually missed the whole point. Excuse me. No, I wanted to show that this is true of shell, and then yeah, maybe let me write it in here to make it clearer. So I had I wanted all of these three terms except for the one where I act on epsilon. I wanted to say that these were equal to d mu on dl dd phi is this term, so it cancels, and then I'm left with so dl dd phi plus dl dd phi I times phi j. Right, yes, that's what I mean. So I wanted to all right, so maybe I can say it this way then. this was equal to 0, maybe let's write this specifically. So dl dd phi I, phi j plus dl dd phi d mu phi I delta phi j, right? And then this piece was equal to 0 by the symmetry. So that delta S was equal to epsilon I epsilon A T A times, and further I can call this dl. Well, no, maybe not. Let me write it like this. dl d phi I phi j plus dl d mu phi I phi j plus this term. Okay, and in here, indeed, by the symmetry, this must be just equal to 0, right? Because I epsilon A T A phi j is the variation. And here I also get the same, delta phi j. So this is just from the fact that, the integral must be equal to 0 for whatever epsilon, right? All right, so we get that delta S is equal to this thing, d mu epsilon A j, or by partial integration epsilon A d mu j of shell. Okay, so this is
just a question on this term on yellow. The phi j on the second term shouldn't have a derivative, because otherwise, why there's a...
Oh, sorry. Yes.
Okay.
Yeah. Thank you. Right. That's the whole point. Yes, because it's variation with respect to phi times phi, variation with respect to d phi times d phi. Thank you. Yeah. Anyway, so the point is then that now off shell, the variation of the action is this. It's not 0 anymore because I put epsilon to be depending on x, but has this form. So it's consistent because yeah. All right. So so now let's move on to word identities. Now, word identities are really quantum versions of classical symmetries. These are quantum version of a classical symmetry. So this is really what replaces things like this classical d mu j mu a equal to 0. So this was classical. But now at the quantum level, we know by Ehrenfest's theorem that we should have something like this. Okay, so we want to understand more specifically what we get, and we'll get indeed that something like this is true. But let's derive it. So we said our variation d phi I was equal to I epsilon A T A I J phi J. And this was phi prime I minus phi I. And let's consider the path integral d phi, integral d phi e minus s of phi. And in it, I just rename the variable, rename phi prime. So that does nothing. Right? However, I want this phi prime to be this one, phi plus delta phi. But this is an identity, whether integrator of phi or phi prime is the same thing, right? However, what's not obvious is that now, if I have the Jacobian to go from d phi to d phi prime to be equal to 1. So this is a linear relation, right? That's the point of a linear symmetry. It's delta phi is proportional to phi. Okay, so the Jacobian, if we're not in quantum theory, the Jacobian would be 1. So it's something natural to think that this would be 1. However, we will see that, in fact, quantum anomalies occur exactly when the Jacobian from d phi to d phi prime is not 1. Okay, this is a very important, well, we will see now. We will not see unless you take quantum field theory 2 with me, but anyway, so it happens. So quantum anomalies really means what you expect it to mean given this, that you have a classical symmetry and it's not respected at the quantum level. So we will obtain, in the case of anomalies, we will obtain that d mu j mu average is not equal to 0. And that's a peculiar thing, but that happens really because of this Jacobian. Alright, but for the moment, ignoring this subtlety, we say that if this is true, then I would write this as integral d phi e minus s of phi prime. Right? And now, subtracting the two, I say that integral d phi e minus s of phi prime minus e minus s of phi is equal to 0. Or this is delta s of phi under the symmetry e minus s of phi. Right? Because remember, phi prime for me is phi plus the symmetry variation. All right. But now I want to use this that I just said, namely the variation of the action under a local form of the global symmetry. So I should say under a local form of the symmetry. Okay. And then, as we just saw, this was integral d mu epsilon times j mu. So, or by partial integration, I could write it like epsilon I epsilon times d mu j mu. So this is, well, I integral d phi or minus I d for x, which I can put outside, d for x, epsilon a of x, integral d phi, here e minus s of phi, and d mu j mu a. Okay? But now epsilon a of x is arbitrary. Well, it has to fall off at infinity, but other than that it's arbitrary. So I can peel off this integral because I have inside multiplying an arbitrary function. And then I can say that really I have the local equation d phi minus s of phi d mu j mu a of x equal to 0. And as we see in the path integral formalism, this is what we promised that should be the case given the Ehrenfest theorem. This is, in other words, just d mu j mu a on the average being equal to 0. Right? And this is, or something coming from this and other things like this, will be called word identities. The first observation is that I can consider also another operator some A that depends on the set phi I, some operator, and then its variation, since the function of phi i's can be written as integral over x variation with respect to phi of x, with respect to epsilon, because epsilon acts on phi, and then times epsilon. And then I basically insert this operator A in all the things that I did. So I put an A in here, A in here, A in here, and then A in here, and A in here. Right? Sorry. No, let me not. So only up to here. So then what I get is 0 is integral d phi e minus s of phi a of phi, where I vary this product, e minus s times a. Right? This is what we do. And but then I have two contributions. One from varying the action and one from varying a, which is also a function of phi. Right? So I have the contribution where I vary s, where I just multiply by a. This I already know what I get. I get this epsilon times d mu j mu. So let me write it even on this integral d for x epsilon n of x, and then d mu j mu a of x times a of phi e minus s of minus s of phi. And then I still have this term, right? So So I said that A is varied with respect to epsilon A as well, and then multiplied by epsilon A. So this integral d4x epsilon A was given a common factor. I also gave a common factor, a factor of I, so I have to cancel with a minus I. So I have minus I times dA d epsilon A. And then this is multiplying E minus S. So, so then I get a more general word identity. So as before, I can peel off this integral because inside I have the arbitrary function epsilon A of x. So I write just the path integral of this being equal to 0. And I write it as two terms. So the first term is this one. So integral d phi d mu j mu a times e minus s of phi. Then this is equal to I times path integral with e minus s of phi of dA d epsilon a. Okay? So this is also a more general set of word identities. So I can write this then formally as d mu a is equal to I del A del epsilon A. Okay, so this is a type of word identity, a more general type of word identity. And well, in particular, among the possible A of phi's, I can also put a source factor. Right? So if I put a source, then the right-hand side of the word identity is wait a minute. What did I write here? I'm a little bit confused. Well, okay, so yeah, so I can write the one with the word identities with J, but with a current like this. But we can also derive things from the beginning. So that is to say, write that the variation with respect to epsilon of A of this new term. So what I was doing before was writing that 0 is equal to the variation of the variation of this factor, right? So I put the factor A to be equal to exponent j dot phi, which amounts to adding this thing in the exponent, right? And then the variation itself, I can divide by epsilon A of x, which is what I'll do afterwards also. But now I want to write this, taking into account that this is a function of phi. And when I vary respect to epsilon, I first vary respect to phi, and then the variation of phi is ITA times epsilon, which I will cancel. And so in here, I'm left with well, minus s plus phi j times so variation of s with respect to phi, minus s with respect to phi, times variation of phi, but then I've written ITA epsilon, that cancels, I'm left with just phi j. And then the same thing for this second term. So this is phi times j. I vary with respect to epsilon. So I got I, t, and epsilon outside. Now I'm left with just another phi. So this would be, as before, j phi. And finally, now in the last step, I can do what I did before. And when I see, since now I have this exponent with j phi, I can replace the phi outside with derivative with respect to j. Because derivative with respect to j, acting on exponent will give me the phi. Right? So I can rewrite this as ITA ij integral d phi minus ds d phi I minus s d phi, and I also want to no, sorry, this was phi j, not phi. Because I replace the variation of phi I is epsilon t phi j. And here I can take both phi j's, take them outside of the bracket. So here I write d minus dd minus delta s d phi I, where phi I is replaced with ddji, then plus ji. Then outside the bracket I still have the phi j, which now I replace with ddjj. E minus s of phi. And as always when we did these tricks, these whole terms depend only on j, plus j phi. Depend only on j, so they get outside the path integral. So this is j minus ds d phi I is ddji plus ji and ddj times z of j. Okay. And so, from this form of writing it, we see now that, so if I take further derivatives, take more ddj's, I will get, like for the Dyson-Schwinger equation, I will get an identity between various endpoint functions, right? The derivatives with respect to j of z of j is give us green functions, endpoint functions, and there are different number of derivatives. So in here I have the variation of the action with a where I replace phi with a number of ddj. So here I'll get more derivatives, so a higher input function than here. So like for Dyson-Schwinger, we'll get relations between Green's functions. Okay? So these word identities, which come from global symmetries, in the end give us also relations between Green's functions, the same way as the Dyson-Schwinger equation did. All right? And also, like in the case of Dyson-Schwinger, we could write equations both for the full Green's functions, like it comes from here, but we can also redo the formulas for connected functions and for 1pi. And finally, let me say that word identities are very important in quantum field theory. So as we see, these are reflections of the symmetries onto the Green's functions. So they will reflect the global symmetry into the form of the Green's function. So let's see word identities. If you want restrictions on the form of Green's functions from symmetries.
Why
Right?
are you only saying global symmetries if you're using space-independent absolute?
Right, but this was what I started with. So I said the point was the symmetry itself was global, so delta S is 0 for the global symmetry, right? But if I promote it to a local one, delta S is not 0 anymore, and then from it I can get these equations, right? Okay. All right, but the point was that in order to derive this, I had to have a global symmetry. So one not so good perhaps example, because
So the symmetry remains in a local way. You have this.
well, no, I mean the point is the Green's functions are functions that depend on various x's, so they are local in some sense. But this one is just a reflection of the global symmetry onto the Green's function, so it just restricts the form of the Green's functions. And unfortunately, so I didn't want to give random examples. I wanted to give just the simplest example that we already discussed, which is electromagnetism. But that's a problem because electromagnetism has only a local symmetry, and as I said, for the nutter here, we need a global one. So the analogy that I'm going to give now, it's not perfect. But for QED, the analog of the word identity, well, word Takahashi identity in this case. We'll see this later on in this course. Will restrict the form, will restrict the form of the two-point function in particular. So if I have gauge invariance, then that, as we know, must be fixed by the best way to fix it is the Lorentz gauge, d mu a mu equal to 0, which amounts to, in momentum space, k mu a mu of k equal to 0. So, but the point is, this comes from gauge invariance. And it turns out, if you follow the formalism in the case of this local symmetry, that the corresponding action of the gauge invariance on the 2-point function, actually the 1pi 2-point function, pi mu, about which we talked about before, is as if the external legs were a mu's, right? If the external legs were a mu's, you expect them contraction with k to be 0, and that's what happens with pi mu. And in particular, if I have this, you see this allows us to solve for the tensor structure of pi mu of k, to reduce it to just a scalar function. Because this then must be equal to this Lorentz structure. That's the only one. This is a function of k, so that's, and it's a massless theory. It doesn't have any other scales. So the only possibility is this one. So you see the, well, in this case, this local gauge invariance has, on the Green's functions, has the implication of this set of constraint equations, which in turn allow us to solve for the tensor structure of this object. Okay? Now, for a true global symmetry, you cannot do that as much as here, because here you reduce the tensor structure to just a scalar, just because you know, k is the Fourier space replacement for x. So basically, because you have a symmetry at every k or every x, you are allowed to do this. Now, in the case of global symmetry, it's not so constraining, but still you can say something about the form of the endpoint functions. You can still reduce it a little bit. So that's that. All right, so this is everything I want to tell you today. Do you have any questions? No? All right. Yeah, then maybe we can stop with this.